Good afternoon all. Welcome to the another lecture of electronics, semester one, electronics, and in which we were studying some of the basics of electronics. And I guess yesterday we have studied about the resistances. Um, yeah, just hold it for a second. Yeah, we have understood about the resistances and their parameters. We have talked about some of the fundamentals of resistances. Yeah, so yesterday we have studied about some basics of electronics and some basics of resistances as such, and today we are going to continue with the same. So let us start with that. Let me share my screen. So yeah, yesterday what we have studied was the color codes of say resistances, and in that, yeah, I hope my screen is visible to you all. You can.
Yes,
Thank you, Peter. Thank you very much. So keep me updating, and I was expecting your feedback on that. So please keep me reminding if I am unable to hear or audible. So let us start with us. Today we are, you know, my introduction. Let us introduce for the new students who have come for first time. Myself, Dr. Andy Meshram, sir, from Head of Department Electronics, and I'm responsible for everything in electronics over here. So today we have to start with some of the basics of resistances, right? So we have yesterday studied some basic concepts of current, voltage, and the resistance. That was Ohm's law, right? The derivation of Ohm's law. And we have continued with it for the resistances. And yesterday we have also studied how to calculate the value of resistance by using the color codes. So today also we will just go through that and just brush it up what we have studied yesterday. So resistor examples, these were some of the resistances, uh, the types of resistances and what actually they look like. So these are resistances that we have studied. This is the symbol of resistance over here. And these are the power ratings of resistances according to which we connect this resistances to a circuit, right? So these are some of the resistances which are shown, and these are actual diagrams of those resistances, actual photos of those resistances, and these are resistor labels. Yeah. So we are having wire wound resistances and all, and how to calculate the value of a resistance by using the color codes that we have studied yesterday. So I have told you that in a resistance, there are usually 4 to 6 bands. That those are colored bands on a resistance, and according to which we can calculate the value of a resistance. Say in this example, what we have done is there are 4 color codes over there. So we have written there A, B, C, and the fourth one is for the tolerance. That is written as TOL, right? So in all, there are 4 bands in this resistance, and according to which we are going to calculate the value of that particular resistance. So this is that, and what we write is AB. So first band, second band, for the number of the first band and the second band is written in conjunction, and then multiplied by the number of the third band to the power of 10, right? So, and the fourth band gives us the tolerance. That is how much tolerance the particular resistance has. That I have told you. We'll talk on that also. So let us calculate. And to calculate this, the resistor color codes, we have this formula that we call it as BB Roy of Great Britain got a very good wife, right? So in there, the first alphabets, the first block letter alphabets, that is BB Roy, ROY, G for Great Britain, B for Britain, V for very, G for good, and W for wife. So these all are 10 alphabets that we are going to use, and according to that we can have the color codes. The first B is for the black, that is written for 0. Second B is for brown, that is given a digit, that is number 1. Then we have Roy, ROY, R for red, O for orange, Y for yellow. And accordingly, we have the colors 1, 2, 3, 4. The for Great Britain, we are having green G for green, that the number is 5. Then Britain B, that is for blue, so the 6. And then we have violet, that is V. So this is not purple, this is actually violet. So that is written over there. We can also change that. Little bit. Let me change this. So this is violet. Yeah. So this is violet. Uh, so violet is there on the seventh number, and then the next one is G again, that is for gray, and the last one is W, that is white. And the fourth band consists of white, silver, gold. There might be red, there might be brown, and according to which we decide the tolerance. Tolerance means what is the actual resistance and what is the fluctuation of that particular resistance can be checked by using this tolerance band, right? So these tolerance bands are like here, brown, red. Brown gives us plus minus 1%. I hope you will not be able to set this fourth band. Well, there are some, so they are very precise and particular about the resistance. The red one is having plus minus 2%. Then we are having gold plus minus 5%, silver plus minus 10%, none. If there is no band, the fourth band is, if there the fourth band is missing, then it might be having plus minus 20% tolerance, right? So what that tolerance means, that what is the effective resistance of that. If I guess, if say the resistance value is calculated like 100 ohms, then if it is having the fourth band as silver, then it is having plus minus 10%, which means that 100 plus 10, that is 110, and minus 10 means 90. So the resistance may vary from 90 to 110 ohms. It will not show you actual 100, right? So it may vary, and that particular 10 is decides what is the tolerance. So in that case, if there is no fourth band, then the tolerance will vary from 20% plus minus 20%, which says that if the resistance is calculated as 100 ohms, then it may vary from 80 to 120. So this much of variation might be there by calculating the resistance of that. So this is for the tolerance, and this is how the color codes are being written over there, and these are the multipliers which we have to connect them raised to power. So let us start with this example. The first example which is shown over here is having the first digit as yellow, second digit as violet, third digit as red, which is actually the multiplier. So what we will do is we will add this. The number of yellow over here uh, is 4, right? So number of yellow is 4. So we'll write there 4. And the number of violet is 7. So we'll write 7. And the third band is red, which has the number that is 2. So we will have that multiplier as 10 raised to power 2. So the total number can be written as 4, 7, that is 47, multiplied by 10 raised to power 2. So the total resistance will comes out to be 47 into 4,700 ohms, right? And if we calculate in terms of some, say, units, like, so we can calculate as if we shift this for zero point 0.1 decimal, so it will be 4.7, and this will be multiplied by 10 raised to power 3. So we'll have 4.7 kilo ohms resistance, right? This is how it is being calculated. Now the tolerance is, now gold is there, the fourth band is gold, so the tolerance will be plus minus 5%. Yeah, one more thing. Just keep on taking the snapshots of those things so that you will have some notes also. And if you are able to write something on your notebooks, that will be far better for you to understand, right, at some level. So yeah, so we have done with this, how to calculate the resistances. Let's offline classes start, and we will try to make that practical, practically calculate your resistances. So yeah, that is there. The second most important thing in connection with the resistors are when they are connected in when the resistors are connected in series, the resistance of both of them are being added, right? So let us see how we connect it in series. What it implies that we are connecting it in a series. So this is how a series combination looks like. So we are having this resistance R1 and this resistance as R2, and they are connected in series. So this is one point, this is the second point. The second point of one resistance is connected to the first point of the second resistance, and the second point is kept. And the output resistance is taken across these two, right? So this is a series combination of that. Always remember, whenever the resistance are connected in series, the resistance are being added, right? So the resistance of both the resistance are being added. In this case, we are having two resistances having 1 kilo ohms resistance. So this is also 1 kilo ohm and this is also 1 kilo ohm. So the series combination value of this resistance, both resistances R1 and R2, will be equal to 2 kilo ohms, right? So this is 2 kilo ohms. So the total resistance of any series combination will be the summation of all the resistances connected in series. So there might be many resistances which can be connected in series. So we can calculate R1 plus R2 plus R3 plus R4, R3, and so on, right? Accordingly, we'll have that the total resistance of that. Now, in this case, we are having two resistances. So the equivalent resistance, the total resistance in series will be equal to 1 plus 1, that will be equal to 2 kilo ohms, right? So this is for the series combination. So whenever the resistance are being connected in series, the resistance of those are being added, right? Now in the second case, what happens when the series resistors are connected in parallel? So whenever the resistance are being connected in parallel, so the combination is like this. So what we are doing is the first terminal is being connected parallelly and the second pin is connected to both. So both of them are in parallel. So this is a parallel combination, that is R1 and R2. One more thing. Remember, there is no polarity of resistance. Polarity means there is no positive, negative. So the resistance can be connected in any form. There is no first terminal or second terminal sort of like they can be interchanged also, right? So you can connect to any of those resistances. So here we are having this parallel combination. So R1 and R2. Since yeah, in the earlier, yeah, there was a 3 milliampere current which was going to flow through this. According to the Ohm's law, we are having 6 volt uh, power supply over here. So this 6 volt power supply is being divided into two parts, 3 volt and 3 volt, because the value of the resistances are equal. So the voltages are being divided equally, right? And this is called as the voltage divider circuit. This is how the voltage is being divided. Now, as far as current is concerned, you are able to see that 3 milliampere current is going to flow through this, right? And this is because we are having the resistance as 2 kilo ohms. So 2 kilo ohms and 6 volt will give us V equal to IR. That means I will be equal to V by R. So V is 6 volt over here divided by 2. So it will give you 3 milliampere current. Similarly, when we connect this resistors in parallel, what happens? The same power supply we have used, that is 6 volt power supply. The resistances are being connected in parallel. And let us calculate what is the parallel resistance, right? So whenever we are going to calculate the parallel parallel combination of a resistor, it is calculated as 1 by R total is equal to 1 by R1 plus 1 by R2. Remember this. This is the basic formula. 1 by R total equal to 1 by R1 plus 1 by R2. And when we multiply those, cross multiply and add, then we have this formula as R total equals to R1 into R2 by R1 plus R2. Remember this. R total equal to R1 into R2 by R1 plus R2, right? And in this case, what happens if both the resistances are equal? So 1 into 1, that is equal to 1, and 1 plus 1 is equal to 2. So that is equal to 1 by 2. So 1 by 2, that is 0.5 kilo ohms. So half of this resistance. So remember this, whenever the resistance is connected in parallel, the resistance, the total resistance of the combination decreases, right? And that decrease is always is always विनय बेटा वो मिटा दो उसको लाइन को, is always less than the smallest resistance connected in that combination. Remember this, what I've told you. Always, whenever we connect a resistance in parallel, the combination, the resistance, the total resistance in combination will be less than the smallest resistance in the connection, right? So if else it is having 0.5 kilo ohms, then one of the resistance is 0.5 kilo ohm, then the parallel combination resistance will be less than 0.5 kilo ohms, right? Now, since we are used two equal value resistances 1k 1k, therefore the value, the combination of resistance value has been decreased to 0.5k. And when we multiply, when we divide this 0.5k or voltage by 0.5k, then the output comes out to be 12 milliampere current, right? EI equal to V by R. So V is 6 volt over here, and the total combinational resistance is 0.5k. So 6 volt divided by 0.5k equal to 12 milliamperes, right? So the current flowing through this circuit will be 12 milliampere, right? So this is for the resistances in parallel. Now let us start with us. Yeah, we have studied this metric units and conversions. This is what I have done there, 47 into 10 raised to power 2. So I have just shifted one decimal point. I have made it 4.7, and I have increased the power of 10 by 1. So it was equal to 4.7 into 10 raised to power 3. And that is why how I could say that the total resistance of that particular color code was equal to 4.7 kilo ohms, right? Now what kilo ohms means is 10 raised to power 3. So every time whenever you have this digit, that is 10 raised to power 3, or whenever there are written as small k, then you have to understand that it is being multiplied by 10 raised to power 3. Like in on our speedometer, we are having the kilometer range. We calculate the speed kilometers per hour, right? Kilometers per hour, राइट अकॉर्डिंगली 60 की स्पीड है 70 की स्पीड है ये हम लोग चेक करते हैं व्हाट इट इंप्लाइज हम लोग 60 किलोमीटर एक घंटे में रन कर सकते हैं वो स्पीड 60 किलोमीटर पर आवर राइट ऐसा तो दैट kilo stands for 10 raised to power 3 which implies that we are having 1000 meters inside it 1 kilometer is 1000 meters 1000 means 10 raised to power 3 meters right Similarly, there are some more conversions that is pico. Pico is 10 raised to power minus 12. So we'll move from here, I guess. So this is milli. So milli you have heard that is 10 raised to power minus 3. This is the smallest unit. So 10 raised to power 3, that is what we have heard, millihenry, millimeter, or milliamperes current, right? So there we write milli. Micro stands for 10 raised to power minus 6. So again, we are having microhenry, micrometer, microamperes current. That is, those are written as micro. Nano, 10 raised to power minus 9, nanohertz frequency, and gigahertz, sorry, nanohertz, nanoseconds. So time is nanoseconds. Then we are having pico, 10 raised to power minus 12, right? So there are 12 digits after point. So this is for the smallest one, and the highest one is kilo, that is 10 raised to power 3. Greater than that is mega, 10 raised to power 6. And above that, we are having giga, 10 raised to power 9 plus 9. And after this, we are having tera, that is capital T, T-E-R-A, 10 raised to power 12. So this is for the units and metrics that we are going to use throughout our course, throughout our BSc. The next one that we are having here is, yeah. So we will start with some of the basic concepts of digital meter. This is what we were expecting to teach you on in your some basics introduction bridge courses over there. So digital multimeter is one of them. So digital multimeter, how it looks like. So this is a digital multimeter diagram. I guess I'll be having some more over there, so I might show you. So this is digital meter that we are going to use. This is called as DMM, which is called, which is nothing but the measuring instrument, right? So DMM, digital multimeter. Now why it is called as multimeter? Because it is going to measure many parameters. That is why it is called as multi. And it is going to measure something. That is why it is called as a meter. And the output which is going to be there are in the form of digits. So that is why it is called as a digital multimeter, right? So we are having a digital multimeter. Now you should understand how to measure voltage, how to measure current, how to measure resistances. So an ammeter which measures the current. Ammeter is called as a device which is going to measure the current. A voltmeter which is going to measure the voltage. And you are able to see here there are some grooves. So this is this part of the portion which is there, which is showing 1220, 2000 m, 200 m. So this portion is going to measure DC voltage. Here you are being able to see that this is a straight line, and this indicates that it is going to measure DC voltage, and it starts from 1000 to 200 millivolt, right? 1000 volt to 200 millivolt. The second range over here is for the AC voltage, so 200 and 750, which comes at our home. So that can be measured when the knob is kept at this point, right? Then the another portion over here is for the current. Now this is a DC current, which is going to be measured by the multimeter. So this is 200 microamperes, 2000 microamperes, 20 milliamperes, 200 milliampere, and here it is showing 10 milliamperes, right? So this is for the DC current that is going to measure. Then on this portion, we are having ohm meter that is going to measure the resistance, right? So whenever we need to measure a resistance, we can measure by keeping the knob in this portion, right? On the another section, we are having a diode symbol over here, if you are able to see, which is used to check whether the diode is working or not. And the another is here, it is showing like a speaker. So here we are going to check the continuity of wire and all. So for connection, it will show you that continuity. So this is the for the little bit introduction of a digital multimeter. Then we might have yeah. So multimeter is a combination of all the functions, possibly some additional ones as well as single instrument also. So these are there. Some instruments are there too. So digital multimeter, parallel connection. Yeah. For voltmeter, we need a parallel combination. Here are the sockets which we are going to put the probes. So the upper probe is meant for higher current, that is for 10, and the lower currents are being measured by putting the probe over here. So these are the positive probes. Here we can, here putting the probe will give you voltage, say resistance and milli current also. So milliampere current. And the lowest one over here is to put the ground terminal, right? For voltmeter, the voltmeter is always connected in parallel. Remember this, always connected in parallel. The what is it? Voltage is nothing but the potential difference between the 2 points, right? So that is why it is called as, it is always connected in parallel. Ammeter, to measure current, it is always connected in series. Remember this. Whenever we need to measure the current, we have to connect this ammeter in series, right? And for ohm meter, yes, ohm meter, we in, we need to connect it without power supply, because internally it will give you that power. So adjust range, start from highest limit. If you don't know, आपको लिमिट एडजस्ट करनी है, वोल्टेज अगर हाई जा रहा होगा तो आपको नीचे नीचे आना है, so that it will show you that. So this is for the voltmeter. Ammeter connections, this is how ammeter is connected. I have told you that ammeter is always connected in series. So this is how the ammeter is connected. This diagram you have already we have seen this diagram. The resistance are connected in series, and we have to connect, break here wire and connect this two terminals to this ammeter, and the current can be measured like this. So ammeter is connected like this. And yeah, one more thing, for ammeter must have low input impedance. Remember this. The emitter has a low input impedance. What is input impedance? That we will study when we will study the say ideal voltage and current sources. Then that time I will let you know what is it means like impedance. For today, you may understand that impedance is nothing but the resistance of a circuit, right? AC resistance of a circuit. That is called as a impedance. It is actually a resistance, but it is for an AC signal. So this is how emitter is connected. And then how voltmeter is connected. Voltmeter is always connected in parallel. Remember this. So if you want to measure a voltage across this resistance R2, you have to connect this voltmeter in parallel with this resistance. So this is how the voltmeter is connected. Remember, ammeter is connected in series, voltmeter is connected in parallel, right? All the voltmeter is connected in parallel between the 2 points, and the voltmeter should have very high input impedance. Mind this. Why? Because whenever it is connected in parallel, the current may flow through this voltmeter. So it might have a very high impedance so that minimum current flows through that and maximum current flows through the resistances or the loads. Similarly, when we say that we are connecting the ammeter in series, which implies that the current is going to flow through this ammeter, right? So if it has a high resistance, then the current will be blocked over here and small current is going to flow through this load. So to avoid that, this ammeter should have the low input impedance or low resistance, right? So it will have a low resistance. The ammeter should have the low resistance, and the voltmeter will have high input impedance. Remember this. Now the last connection is for the ohm meter connection. So ohm meter is to measure the resistance of a load, right? Whenever you need to measure the resistance, do not measure the resistance in a circuit. So whenever you need to measure that, you have to take that resistance out of the circuit, and then you have to put that meter over there, and you can measure the resistance, right? Even while putting the probes, you don't need to touch your body parts, right? Don't put your hands on that, so that your body resistance will come in parallel with that resistance, and the ohm meter will show you the error in reading. So avoid that. You can have one pin, say, stucking with your resistance, but don't put both the hands over there. So avoid that. So whenever you need to measure the resistance, you have to take out the resistance from the circuit, and then only you can measure the resistance, right? So you don't need power supply, because it is going to use its internal power supply. Must take it out of the circuit altogether and test it separately. So the resistance are always checked separately. So this is all for today's class. I guess you have got this today's class, and I expect that you are understanding this. Uh, Lastly, thank you very much for attending the class sincerely. And if you have any issues, let me know, so that we can resolve those issues. Let me just refresh within a second that what we have studied today. So today we have studied the introduction of say resistances, in which we have studied some resistors examples, some types of resistances, and how to calculate a resistance by using color codes. So this is the formula for that. BROY of Great Britain got a very good wife, and that is the color code that we are having: black, brown, red, orange, yellow, green, blue, violet, gray, white, silver, and gold. These are the four bands, which gives you the tolerance. The tolerance can be calculated here, like so: brown, red, gold, silver, none. So if there is these five bands, accordingly their tolerances are given over there. So the resistor color codes, and this is how we are going to calculate the value of the resistance by using color codes: the first digit, second digit, and first band, second band, and third band, and the fourth band for tolerance. So the first band over here is yellow, so we have taken the fourth digit, that is 4, and the second is yellow, so we are taking it as 7, So 4 and 7, that is 47. And the third band, multiplier of 10, that is 2. So 10 raised to power 2, we will be taking that. Then the total resistance comes out to be 47 into 10 raised to power 2, including plus minus of 5%, that is the tolerance given by the gold band, that is the 4 band attached to there. So that is for the value calculation for resistances by using color codes. This is how the resistances are calculated in series. So whenever the resistances are connected in series, they are being added. So R1 plus R2, and which will give you 2 kilo ohms. Similarly, whenever the resistances are connected in parallel, the resistance decreases, and it is calculated by this formula. R total is equal to R1 into R2 by R1 plus R2. If you don't remember this, remember that 1 by R total equal to 1 by R1 plus 1 by R2. 2. 1 by R total equal to 1 by R1 plus 1 by R2. And by say solving that equation, we get this formula, that is R total is equal to R1 into R2 by R1 plus R2. So that comes out to be 0.5 kilo ohms in this case. So this is some of the metric and units and conversions: pico, nano, micro, milli, kilo, mega, giga, tera. Right? Remember, tera is also there. So that is over there. And the next one is digital meters that we have studied. So this is digital multimeter, means DMM. Here we are going to measure current, voltage, resistance, and say some more functions are there. Whenever we come offline, then we'll be seeing those. So these are the examples. Voltmeter is always connected in parallel, whereas the current meter is always connected in series, and ohm meter is always connected out of the circuit, that is without the power supply of the circuit, right? So whenever we need to measure the resistance, then we have to take the resistance out of that. So this is for there. Then we have emitter connections. Emitter is connected in series. The resistance of the emitter should be low, and the voltmeter is connected in parallel. The input impedance of voltmeter is must be very high. Ohm meter connection, the resistance is to be taken out of that. So these are all connections that we have studied. I guess you have understood that. I'll be putting this video on YouTube. Please go through my YouTube channel and view these videos. And if you have any queries, you can put comments on those things. Even you can give me feedback on this right now. So thank you very much for patience listening. And I guess everything is okay at your end. If you have any questions, you can ask, or if you have understood, we can sum up the class today. So shall we sum up? Yes, of course, I will be putting this on the YouTube channel also. So today itself, I will be putting that. So yeah, so I will be ending the class. Okay. Thank you, Komal. Thank you very much. Have a nice time. Take care. Stay safe. Stay home. Stay safe. Take care. Good day. Bye.